Okay students, welcome to the next portion of linear algebra. In this portion we are going to discuss least squares and min norm. Okay, so today's topic is mainly going to be trying to look at the main linear algebraic aspects associated with these two problems. Okay, so we'll derive the expressions and we'll look at the main properties. The next lecture we'll look at algorithms on how to go about solving least squares, and in the final portion we'll look at many variants of least squares. Okay, so that's the plan. Without much further delay, let's actually start the discussion of the problem. Okay, so what is least squares fundamentally? Least squares is a problem that involves minimizing a sum of squares, okay, where each square inside each bracket corresponding to a square, you have a linear term. Okay, for example, this could be something like 5x1 plus 10x2 minus 3. This could be 2x1 plus 3x2 minus 1, and this could be 5x2 minus 3. Okay, so basically it's a sum of squares where each term in the square is a linear expression in certain number of variables. So here I'm assuming 2 variables. In general you could have n variables, right, where each of these terms here could be a linear expression in x1 to xn. Okay, so there will be some linear combination followed by some constant. Okay, so that's how it's going to be. That's called least squares. Sometimes it's also called linear least squares for this precise reason. Okay, linear least squares meaning that each term here is a linear expression. Okay, but you're taking squares eventually, so it doesn't mean that the overall expression is linear. It just means that the term under the square is linear. Okay, but you could also potentially think of non-linear least squares. Non-linear least squares, but each term here also has some non-linear term. Maybe you could have log of x1 minus 5. You could have cos of x2 minus 3 here or whatever. Right? So that's more general non-linear least squares. Okay, so we're going to work on linear least squares, and the main reference for this section is going to be Boyd's book that I referred to in the first segment. Okay, so this is Boyd et al. Vectors, matrices, and least squares. Okay, VMLS. Okay, the link is there in the first segment notes. Okay, so that's going to be the main text. In particular, we're going to cover part of chapter 12 today. Okay, we're going to also cover a lot of things that are not there in the book. Okay, and we will also not cover everything that is there in the book. Okay, nevertheless, the book is a very good read, especially for students who are inclined or who are registered for the AI courses. I think the book provides a very, very good perspective of least squares for data science. Okay, so chapter 12 is what we're going to focus on today. So please start reading chapter 12. Okay, we'll not cover all the chapters on least squares from that book, but I'll tell you which portions of the book as we proceed in the lectures. Okay, so in the linear least squares problem, this is what we have, right? So this is an expression like this, right? So in general, you can say that your expressions are like this, right? So it's like a1 transpose x. So let x be the vector of variables. So it's an n cross 1 vector where each entry in x is a corresponding variable, just like we did in quadratic forms, right? So let's just vectorize this, right? So whole thing we write as a vector x, right? And these coefficients we collect in the vector a1. Okay, so we have a1 transpose x is an product, right? Okay, so this minus b1 whole square plus a2 transpose x minus b2. So b2 is just a scalar here. b2 whole square plus 1. That's what we're going to get. Okay, so if we look at the terms here, simply a1 transpose x, a2 transpose x, if we construct this matrix a1 transpose, a2 transpose, so on up to, so let's say the number of square terms here is m, right? So here you have m equal to 3, right, in this case, because there are 3 square terms, this and this. Okay, so in general you'll have up to am transpose x, okay, is equal to, so you write this whole thing in the matrix form like this, right, bm. Okay, let's call this whole thing as a matrix. Now this is a matrix because each a1 transpose is like a row vector of size n. This is size n and there are m of them, right? So this is going to be like m cross n matrix. Okay, let's call it A. this is going to be an n cross 1 vector, and this is going to be an n cross 1 vector. Okay? So effectively, you have, not ax equal to b, you have ax minus b. Okay? So what I'm trying to say here is that the first term here, in this expression here, the first term is essentially the first term in this overall vector, right? The second term here is the second term in this vector, right? You can see the first term is a1 transpose x minus b1. The second term will be a2 transpose x minus b2. Okay, so basically what you are doing when you're computing this overall summation here is you're actually taking the norm of this vector. Okay, so basically you are trying to construct ax minus b norm whole square. This is the 2 norm square. Okay, so that's basically the main idea. So whenever you have any expression of this type, it can be written like this, ax minus b whole square, right? And it's often of interest to find the smallest value of such an expression. Okay, what will be the smallest value of an expression like this over all possible values of the variable x? Okay, that's why it's called least squares. Okay, so the least squares problem is formulated as follows: find minimum value of ax minus b whole square when a and b are given. Okay, so a is m cross n and b is n cross 1. They are both given to you. Okay, fine. So that's what we are going to try to investigate in this lecture. Okay. You also usually when you people ask you to solve such a problem, they don't just want you to find the minimum value. They usually also want you to find the minimum, meaning the x value, the value of the variable vector x that actually achieves this minimum. Okay, so you usually want to find both. Okay, so just like in a single variable case, let's say you are trying to minimize some function like this. Okay, you want to find the minimum value that's given by the y coordinate here. This is the minimum value, but you also want to find the corresponding variable x star that achieves that minimum value. Okay, so that's what we're going to try to do in this lecture. Okay, so the issue is now let's try to do some very preliminary analysis on this problem. Okay, so first, what if a is square invertible? Okay, what if a is square invertible? Okay, so if a is square invertible, then you could actually potentially make this least squares expression to be equal to 0, correct? Because this is actually the sum of squares, right? The smallest possible value it can take is obviously 0, right? And when a is square invertible, you can actually make it to 0, right? So you can just pick x star to be a inverse b, correct? Just pick x star to be a inverse b, then the expression here ax star minus b norm square is actually going to be equal to 0. Okay, so that is the simple scenario. We don't even have to do anything here, right? If a is square invertible. Okay, what if a is fat? Okay, so when a is fat, that typically means m is smaller than n, right? So m is smaller than n, meaning in your A matrix you have very few rows and a lot of columns, right? Then also you can see that this system of equations ax equal to b is basically an underdetermined system. Okay, it's an underdetermined system, right? In fact, if you throw in the assumption that a is fat and full rank, okay, just for simplicity, throw in the assumption that a equal to fat and full rank, then you know that ax equal to b always has solution. In fact, it has infinitely many solutions. Okay, that follows from an intuition, right? Because your variables, the number of variables here is n, but the number of equations is m, which is less than n. It's an underdetermined system, right? So there is always going to be a solution to this problem. So I can always once again pick my x in such a way that ax equal to b. Okay, so pick x star to be any solution to ax equal to b. I can pick x star to be any solution to x equal to b. In this case, once again, I make the least squares term to be equal to 0. Okay, even here there is nothing for us to do, right? You just have to solve the system of equations using whatever. There are many methods available to solve systems of equations. Okay, so there's nothing much for us to do there, right? So by the way, how do you solve a system of equations like this? You can use anything. You can use LU decomposition, you can use QR decomposition. I will discuss a bit of this when we do algorithms in the next lecture. Okay, fine. So the case that is very interesting for us to consider is skinny. Okay, also fat and non-full rank, but that will actually follow in a very similar discussion. We will not discuss that, right? So we'll assume A is skinny. Okay, so that means M is bigger than N. We have way more rows than we have columns in the matrix A. Okay, and for simplicity's sake, once again I'm just going to assume that A is skinny full rank. We'll discuss what happens when it's not full rank and all that stuff later in the lecture. Okay, so let's assume A is skinny full rank. Now if you look at the system Ax equal to B, that may not have a solution, right? So remember here the columns of A, each column of A is going to be so here if you treat X as your unknowns, there are n unknowns, but there are m equations, right? And m is bigger than n, so you have way more equation than unknowns. It's an overdetermined system. It may not have a solution, correct? Because when you have more equations than unknowns, those equations could be inconsistent. You may not actually get a solution, right? So in that case, I may not simply be able to say pick any solution of Ax equal to B, because Ax equal to B does not have a solution in this case, correct? Okay, then what do we do? Okay, so then the idea is to find the minimum value of Ax minus B. Okay, then this least squares problem makes sense, right? In all other scenarios, least squares problem is in some sense trivial, you could say that, right? This is a scenario where it makes sense. The minimum value is actually not going to be 0 here, because Ax equal to B in general will not have a solution. In some cases, it may end up having a solution, right? We'll look at that right now. Okay, fine. So there are many ways to approach solving this problem, right? So one approach, and usually the simplest approach, is to use calculus. Okay, so we have a function here that you are trying to minimize, and it's very natural when you're trying to minimize functions, just take their derivative and set it to 0. Okay, this is the standard approach you will take in other courses. Okay, which is why I'm not going to focus on this approach in this lecture and in this course. Okay, the standard approach, however, we have to remember is to take the derivative and set to 0, right? Here you have many variables. This vector x could have n, right? It has n variables in general, right? So you have to take the partial derivatives with respect to each of these n variables and set it to 0. Okay, and then you can find the optimum, and then you can argue by computing the second derivative that the optimum is this approach will take in another course, for example in optimization or basics of machine learning. In one of those courses you will actually try to approach this problem from that perspective. The other approach we already discussed is to actually treat this as a quadratic function. Okay, meaning that we already discussed that when you have norm and norm square, the natural thing to do is to actually just write it as transpose. So we'll just write it as b minus ax transpose times ax minus b, expand the whole thing, and that resulting thing will actually be a quadratic function, right? And then you can minimize quadratic functions with the trick of completing the square. Okay, in a previous lecture, in fact one full lecture was devoted to how to minimize quadratic functions, right? In that case, you can actually directly write down the expression, and we did that, right? I think it was lecture 6 or something like that. No, lecture 5 I think. You can directly write down the expression, and then that gives you the expression for least squares. Okay, we are not going to focus on that also, right? Here we'll actually look at a more geometric approach to obtaining the same result. We did a bit of this in the first segment, but as usual with most things in the first segment, it was very rushed. Okay, we'll try to make a more detailed, detailed approach here. Okay. So what is the geometric approach here? So geometric approach starts first from the interpretation of matrix product. So if you look at Ax, right, recall that Ax is a vector that is a linear combination of columns of A. Okay, so it's a linear combination of columns of A. So for abuse of notation, let's say just call the columns of A as A1, A2 to An, right? So A has n columns, it's an m cross m matrix. Each of these columns has m coordinates, right? So each of these columns has m coordinates, correct? each of these columns has m coordinates. So that's why you have an m cross n matrix. M cross n matrix. Okay. And when you multiply it with x, right, x1, x2 up to xn, what you get is essentially x1 times a1 plus x2 times a2 plus xn times a. Okay. So the expression that you have here, ax, the expression ax that you have here is actually just going to be a linear combination of the columns a1 to an. Okay. No matter what x is, right? No matter what x is, this vector ax is always in some sense going to be in the span of the columns of A. Okay, all these concepts we have discussed before, right? So this ax is always a vector that's going to be in the image space of A. The span of the columns of A, we give it a name, we call it the image space, correct? So ax is always going to be in the image space of A, correct? So B, however, may not be in the image space of A. That's the main issue we are having, right? So when you have ax, this is a quantity that can only be in the image space of A, right? Whereas B here, a vector that's potentially not in the image space of A. Okay. So what we're trying to do is we're trying to make ax as close to B as possible. By taking x to be different values, you'll get different points in the span of the column space of A. You'll get different points in the span of the columns of A, right? You get different points in the column space, right? B, however, may not be in the column space. So the main idea is how do you pick a vector in the column space of A that is closest to B. Okay, that's the main idea behind the geometric interpretation. Let's look at this figure that I prepared. So this figure is also there in your textbook. We have in vectors, matrices and d-squares. So here for simplicity, I have assumed that A has only two columns, right? And these two columns are represented by these two vectors. So assume we are in a three-dimensional space, meaning here m is actually 3. Okay, so A is a 3 cross 2 matrix. Okay, so each of these A1 and A2 are 3 length vectors. So 3 lengths and 3 length. Okay, it's a 3 cross 2 matrix. So A1 and A2 are both vectors like this. So basically, no matter what x I pick, I will actually only get a point in this plane. Correct? Because I am only going to get some combination of A1 and A2, right? So I am going to get A1x1 plus A2x2, and that's always going to give me some point in this plane. Okay, I am not going to get out of the plane no matter what x I pick. And this B vector can potentially be out of the plane somewhere here, right? Then how do I find a vector on this plane that is closest to B? Okay, what I will do is I will simply drop a perpendicular, okay, from B onto this plane, and then I will look at the point, right? Where does that perpendicular intersect the plane? That is going to be the point on the plane that is closest to B. Okay? That's the fundamental idea. Okay? And this is going to be my x star. Okay, so ax star, okay, is the point on the plane that is closest to B. Okay, and that must be such that this perpendicular vector, and by the way, what is this vector? This vector is going to be just B minus ax star. Okay, B minus ax star, this vector must be orthogonal to the space. Okay, must be orthogonal to this space. So in particular, this vector B minus ax star is going to point vertically. That must be orthogonal to both A1 and A2. Okay, so in other words, B minus ax star must be orthogonal to all the columns of A. Okay, so that's the main idea. Okay. So B minus ax star must be orthogonal to all the columns of A. Okay, must be orthogonal to all the columns of A. Okay, so this in some sense is the error, right? We can call this the error, right? Error must be orthogonal to all the columns. So in other words, it must be orthogonal to IM. Okay, so let's actually look at this. So let's just recall once again. I'm assuming that the columns of A are given by A1, A2 to AN. The example I just considered is for n equal to 2, right? I want B minus AX star, right, to be orthogonal. So that means I want it to be the inner product with the first column must be 0. The inner product with the second column must be 0. Okay, and so on. The inner product with the nth column must also be 0. I'm just writing down what I observed geometrically, right? The products must all be 0. Okay. Now once again, this is a set of n equations. N equations. Yeah, because they have a1 to an here, right? a1 to an. This set of n equations can be written very succinctly as A transpose times B minus AX star equal to 0. Okay, because this matrix A transpose itself is going to be like this, right? A1 transpose, A2 transpose, so on up to AN transpose. Okay, that's what this matrix A transpose is, right? It's a matrix with rows as the corresponding columns of A. Correct? Right. So this is what you will write it as, right? Now once I do this, I simply get A transpose B is equal to A transpose AX star. Okay, that's what I will get. Fine. Now what have we done here? Now it may seem like at the end what you did is you simply started with AX equal to B and you multiplied by A transpose on both sides, right? Effectively it seems like that's what you have done. Okay, but actually a lot more has gone on than that. Okay, so A transpose B equal to A transpose A times X, right? Now this matrix happens to be a square matrix. So this is n cross n square. Unlike earlier, it's a square matrix, and this matrix is an n cross 1 matrix. This whole thing is again an n cross 1 matrix. Okay, so this matrix is an n cross n square matrix, and luckily we hope that that matrix is invertible, right? Then I can simply write X star is equal to A transpose A inverse A transpose B, and we are done. Okay, we are actually found the optimal X star. Okay. Now, is this matrix invertible? Can we actually make that assumption? Well, it comes from assuming full rank. But this is where we are using the full rank property of the matrix, right? So I told you that we're going to assume A to be skinny and full rank. Okay, and this full rank assumption, when A is full rank, then A transpose A is invertible. We have seen this in the first segment, right? A transpose A will actually be invertible, and you can write it like this: A transpose A inverse A transpose times. Okay, so this is going to be the solution to the least squares problem when A is actually skinny and full rank. Okay, so what is interesting here is that this set of equations always has a solution, whereas this set, the initial set of equations, Ax equal to B, may not have a solution, right? But A transpose Ax equal to A transpose B always has a solution. That's what's interesting here. So that's why I said a lot more has gone on here than just multiplying by A transpose on both sides. Okay, fine. So this is the expression for the solution to the least squares problem. Okay, so we will so this idea of using the geometric argument, okay, is always sometimes called the orthogonality principle. Is useful in many other contexts as well. The orthogonality principle primarily says that error is orthogonal to data. I'll explain what these terms mean in a minute. So error here is B minus AX star. Okay, so let's say you're trying to, so in some sense here what you're trying to do is you're trying to write B in terms of the columns of the matrix A. This is not, so I'm trying to write B as x1 a1 plus x2 a2 plus so on plus xn an. You are trying to force B as a linear combination of columns of A, right? What you are saying is the error in your ability to do that. Okay, the error in the difference B minus AX must be orthogonal to data, and in this context what we usually mean by data is the columns of the matrix. Okay, so this analogy usually is very useful in estimation, in statistics and things like that. So in another course in probability you might actually have seen this already. So estimation, this principle is often used to derive the results. Okay, because in the estimation context, you may not have the problem directly as a matrix formulation, right? But it's a very similar idea even there, right? So the main idea is you formulate the error, and then you say that the error is orthogonal to data. Data meaning, so here A1 to AN are treated as data, right? So effectively you are trying to write your measurement B. So as I mentioned in another class, B is usually measurement, right? You are trying to express your measurement B in terms of the data that you already have, A1 to AN. Okay, and you are trying to find the coefficients x1 to xn that best allow you to write your measurement in terms of the data. Okay, so in that case what you are saying is the best way to pick the coefficients x1 to xn is to make sure that the resulting error, will be orthogonal to the data. Okay, it's called orthogonality principle. Is extremely useful way to remember what we have actually discussed here. Okay, fine. So this is the so in the next part we'll go into this derivation slightly in detail, and then we'll introduce the concept of the pseudo inverse.